So Newton's third law is a really quick and simple one. For physicists, it causes all sorts of quandaries, but for everyday applications for things like sports science, it's less worrisome. So basically the idea is that every force has an equal and opposite force. Now, where this comes into play is the understanding that you can't push something in one direction without yourself being pushed back. And that's the practicality of it. If you throw a ball, you will also experience effectively recoil. If you push a sports player, you also get pushed backwards. So if you push an ice skater over, it's very likely you're going to slide in the opposite way. They fall over, you may also fall over. The effect of this can change depending on the two objects and how much friction they're experiencing, but all of that starts to get quite conceptual quite quickly. It does enable somebody, for example, with rubber shoes on a slippy lino floor to push over somebody who's in their socks, while the person with the rubber soles on their shoes doesn't slide at all. But the force is still there. The effects of those forces might be slightly different. Okay, so just one little thing to be aware of. The equal and opposite force has to be the same type of force. So don't fall into the trap of thinking like this box on the table, that the normal reaction force and the force of its weight are equal because they're equal and opposite forces. They're not. When it's on the table, the object experiences weight down and a normal reaction force up. But they are different forces. The normal reaction force up, the equal and opposite effect of that is the box also presses on the table. So the box presses on the table presses on the box. That's a pair of forces. Gravity pulls the box down, the box also pulls the earth up. I know that seems really strange, but it is true. So that's also a pair of forces. So in any given situation like this, there's usually 4 forces involved. The force is always there. So if we do like the animation's doing here and then suddenly remove the table, or the table breaks because it can't hold the weight of the force, the upwards force, this normal reaction force here, disappears, but the weight doesn't. The box accelerates towards the floor, and then when it lands on the floor, it gets a whole new normal reaction force. So the opposite force to the weight is always there. The box always pulls the earth up, the earth always pulls the box down. The normal reaction force is the table pushes on the box, but that means the box pushes on the table. So if the box is too heavy for the table, it is the equal and opposite, the other pair of that reaction force, that breaks the table. Again, I'm getting a little bit conceptual with this one, and this isn't a really important idea you need to understand, but it's very easy to understand the rule, but misinterpret it and think that objects don't move, or that the equal and opposite thing means that an object will just stay still. And obviously, if we took the table away in this case, if that was true, the object would just float in midair. And I hope we know from observation that that doesn't tend to happen.